Good afternoon, everyone. Today I'm going to continue the same topic which I taken in the previous class. That is solvents. So in previous class we discussed, we studied about what exactly the solvent and like how exactly solvent really plays in an biological systems. These all things we studied. For instance, I can give example. Solvent indicates first and foremost thing comes to our mind that if solvent means simple is water, right? So if we consider water as solvent, our body is made up of 70% of water itself, as you all know that. And water is required for the generation of the cells, to activate the cells within the human body. So once the cells get activated, the person is going to get have more energy to do their regular work like that. So solvent is one or the other way. It's very important in all the phenomena, especially in chemistry. And we can observe the solvent like in various applications. Example, I can give some examples. You know, if you're using nail polish, the acetone we are going to use to remove that the nail polish. So that is also acts as a solvent. And if I give one more example, that is paints. In paints also we are using the solvents, that is turpentine, what we are going to call it as. So like that, the various applications will be having this particular solvent. So with this context, we studied what exactly is solvent, then what are the types of solvents. Then we have studied according to Loring-Dort state theory, we studied some types of solvents. So which particularly includes, if we talk about the types of solvents, first we'll once again revise the things that what exactly solvent is. Solvent is the one which really does makes the solute to get dissolved in that solvent and make it as a solution. So this definition we already studied in the previous class. If you talk about the different types of the solvents, one is ionizing solvents and another one is non-ionizing solvents. Exactly that indicates, once again, I'm just recalling you people to have a clear idea about this ionizing and deionizing so that it will really help you to understand the concepts which I'm going to discuss in the upcoming section. So ionizing solvents are the one who really ionizes, gets H plus or H minus is going to get supplies. That is ionizing solvents. Again, example as water itself, H2O. Again, non-ionizing solvents also comes. If we talk about the non-ionizing solvents, the solvent which do not undergo auto-ionization, we are going to call it as a non-ionizing solvents. Example I have given, you take any organic solvents like carbon tetrachloride, benzene, hexane. So these are all we are going to categorize under the non-ionizing solvents. So this is what we studied, right? Yeah. So then, if we talk about the types of solvents according to Lori-Bronsted theory, we talk about the acidic solvent, then basic solvent, then we talk about the protic solvents, aprotic solvents. These are all concepts we studied in the previous class. So to highlight these few points, those who have not taken the points, we just take now itself, those who are absent in the previous class, and which is really important to understand the few concepts, especially in chemistry. As I told you, that if you come to the laboratory, then we are going to use multiple types of solvents. So each solvent is having a particular characteristic nature with a particular substrate material. So we cannot use all solvents. As I told you, I'll give a simple example. Chromatography, you already studied in your Q itself. So in chromatography, if you are taking the organic material upon the silica substrate, then we are going to use the appropriate organic solvent to make the solute or make the analyte to get separate from each other, right? So it all depends on the particular type of the solvents is going to interact with the particular type of the organic molecule. Then only the interaction takes place. Then the separation of the analytes takes place upon the silicon string. So this is what actually you studied the chromatography technique. So here also we need to understand the types of like acidic solvent, basic solvent, then polar protic, polar aprotic solvents. So these are the types of solvents are very important to understand the characteristic nature of the any solvents. So in that first one, we'll see that we studied in the previous class, that is acidic solvent. If we talk about acidic solvent, as I already told that, so these solvents have a strong tendency to donate protons. The one which is having a strong tendency to donate protons is indicate that it is an acidic solvent. Acidic solvent. So this indicates what? Strong tendency to donate protons. Strong tendency to donate protons. So this is what? Acidic solvent. So next comes basic solvents. So what exactly this basic solvent is? So basic solvents is nothing but these are the solvents having a strong tendency to accept the proton. Strong tendency to accept the proton. Strong tendency to accept the protons. So this is very important. So now we can easily generalize, right? Which one is acidic the solvent, and which one we can going to correct as a basic solvent, like that. So here we should have a clear idea that according to the Lori-Bronsted acid only, we are talking about the protons. If I want to talk about the electrons in terms of electrons, so that time I would have not used this Lori-Bronsted theory concept over here. Rather, I would use Lewis acid-base theory, but especially organic chemistry, as I told. So you should be very particular when you are dealing with organic chemistry. Majorly we should use the concept of Lowry-Bronsted acid base theory only, because this deals with the in terms of protons, not in terms of electrons. You may ask why we should use the proton concept over here in organic chemistry. Why not electrons like that? So if you are talking about the inorganic complexes or inorganic materials, so there we are going to mainly distinguish the materials in terms of electrons, not with respect to protons. When you are talking about the organic chemistry, we are going to deal with the protons only. So that's why proton concept is very useful in organic chemistry. So we should always talk about in terms of the proton concept. So we should have a clear, if you have a clear understanding about these things, we can really appreciate the solvents in order to apply in the practical applications. So this is about the acidic solvent and this is about the basic solvent. And let us see one more type of the solvent, that is protic solvents. So of course, these are all things I explained in the previous class, but it would be useful for the one who really absent in the previous class. Okay. So before going to protic solvent as well as aprotic solvents, one more type of solvent is there, that is apoptotic solvents. So these are the solvents which really acts as that neither accept the protons nor give the protons. So this is what intermediate between the acidic as well as basic solvent. So this categorized solvent comes under the apoptotic solvent. I can give example, say a simple water molecule itself. So sometimes it acts as both strong tendency to donate protons and strong tendency to accept the protons, depending upon the environment of that molecule. Right? Yeah. If you talk about another concept, that is protic solvents. So as I told that, so protic solvents, so this is another type of the solvents followed by the acidic, basic and apoptotic. Protic solvents, if you talk about the protic solvents, so these solvents contain hydrogen and from which proton can be derived. Got it? Means here we can see the protons, okay, contains the hydrogen from which we can, protons can be derived. Example I can give, I have given HCl. Then one more I can give HF. See, in this example we are finding the presence of hydrogen from which we can derive the protons. So this comes under the category of protic solvents. Now let us see another type, that is a protic solvent. What exactly is a protic solvent? Simple. In a protic solvent, you are not going to find any hydrogen. Hydrogen in the sense what? Sorry. Hydrogen in the sense like the one really electrostatic interaction with the oxygen and hydrogen will not be able to find in these protic solvents. Okay, so this is about the aprotic solvents. Now, so till now we studied the what exactly the meaning of solvents, then what are the types of solvents, and according to the Lowry-Bronsted base theory, we have defined the types of solvent, that is acidic solvent, basic solvent, apoptotic solvent, polar aprotic solvents. These all things we studied. Now let's talk about, if I want to tell this is a solvent, or if I want to say something about the particular item, that should have particular characteristic nature. If I want to call it as a chalk piece, this chalk piece should be made from the material, basically calcium kind of thing that has to be made from this calcium. Then only I can call it as a chalk piece. I cannot call about if I take something like duster, I can take duster. If I call it as a chalk piece, that would be not right one, right? Because If you want to call chalk that chalk should be made up of calcium and that has to be in white in nature or any other color, but it has to, we are going to write on the board and that will be reflected to the visual the persons, right? In a similar way, if I want to call it is a solvent like that, what exactly that solvent should have, we'll study that one now in this section. So under the heading of characteristic properties of solvents, characteristic properties of solvents. So here, mainly we are going to discuss about the four types, or not exactly four types, the four characteristic nature should obey the solvent, or the characteristic nature of the solvent will be covered or will be defined by this particular, subtypes. What are those types? Let us see. First one is boiling point or melting point. Melting point, bar, boiling point. Okay, boiling point. And another one is, that is second one, we should have a clear idea about these things. Latent heat of fusion. Latent heat of fusion or vaporization. Vaporization. Third one, dielectric constant. And the fourth one and the final one is viscosity of solvents. Viscosity of solvents. Yeah. So these are the characteristic features of the solvents. So based on which we can decide that the nature of the solvent, right? In the first one, let us see what exactly this melting point and boiling point of solvent. So as we all know that since from childhood, so for example, 6th, 7th standard, we all studied about the boiling point of the water, melting point of some so and called substance like that, right? What exactly that boiling point or melting point says? If we take water, water usually boils to start at, the boiling is going to start at 100 degrees Celsius, right? So what exactly this indicates? Can you think about this one? What exactly happens? If I take water in a container or in a beaker or in a vessel, if I place on the, under the heat, if I provide a heat, it keep on the atoms or molecules which is present in the water is going to get started with the vibration, is going to start with vibration in the sense they are going to change their state from the stable one to the moving state. So that all the, like before going to heat water, the water molecule is in perfect crystalline nature will be there. Perfect crystalline in the sense all the water molecules will be resided or will be stayed in a particular manner. Like in a particular, if I take a box like this, I take a particular box. I can find only 9 molecules of the water molecules in a perfect crystalline nature, like this. So initially, if we're going to provide a heat to this molecule, we are going to get have this kind of nature. Once if we start to provide heat, so that time the nature of the crystallinity is going to get disappear. So then what happens? The shape or the crystallinity is going to get disappear. So the water molecule is going to start to boil at 100 degrees Celsius. Example I'm giving. Of course, it's true also. At 100 degrees Celsius only, the water molecule is going to get start to bubble. Once the bubble is going to take place, all the liquid material, which really visualize before going to reach the 100 degrees Celsius, after 100 degrees Celsius, it is going to convert into as a gaseous form, right? Gaseous form. So now the state has been changed from liquid state to the gaseous state. Means from one state to another state, to change, to alter, to transfer from one state to another state, the threshold barrier will be there. That threshold barrier will be defined by this melting or boiling point of the substance. Now clear? Example again, water molecule or water. Okay, if I really talk about what exactly the boiling point means, the melting point and boiling point of solvent show that a range of temperature over it which it can exist in the liquid state under atmospheric pressure. Means in certain conditions only, in certain atmosphere only, we can find the state of the liquid in liquid form. If I provide more than 100 degrees Celsius, we cannot see the water molecules, or we cannot see the water in the liquid form. It will be converted into the gaseous form. So like that. So the boiling or melting point, which really gives like under the particular temperature, particular atmosphere only, we can see the existence of the real nature of the solvent. So from which also we can, it is also a characteristic nature of the solvent. Now let us see another type, that is latent heat. Latent heat of fusion and vaporization. So if we really talk about this one, the second one, here in latent heat of fusion as well as vaporization, we should know the meaning of the vaporization. So here also we are going to explain the two terms. One is intermolecular as well as intramolecular bonding, like that. Vaporization is going to start when like when the intermolecular forces is going to become decreases. When the intermolecular force decreases, all the crystallinity is going to get disappears. So then the vaporization takes place. So like that, for a particular material, for a particular substance, but it will be having a particular kind of temperature or a pressure we are going to provide. So under such circumstances only we can find, or we can see the nature of the solvent. So it is what we are going to call it as a heat of vaporization. Okay. So now another term comes, that is dielectric constant. So this also comes under the characteristic nature of the solvent. So what exactly is characteristic nature of that is dielectric constant? Now see, the solvent which is really having the higher dielectric constant. So those solvents can be acts as a better electrolytic solvent than those with a lower dielectric constant. Means if I want to use a solvent for the reaction purposes, so that should be having the higher dielectric constant. So this, based on the dielectric constant, we can see the nature of the electrolytic part. Yeah, what exactly is electrolytic nature? Like the movement of ions. If having higher dielectric constant, then the movement of ions will be more in the particular solvent. So the movement of ions are more mobile in a very fast manner. So the conductivity also is more. If the dielectric constant value is very low, that indicates the mobility of the ions inside, like within the solid, is low. So there we cannot observe any conductivity. So in order to say the conductivity of the solvent, so this dielectric point is also very important, right? So generally, this dielectric constant can be defined with the help of equation C is equal to 1 by D into R plus R. So with the help of this equations, one can give the exact dielectric consternation. Where D is the dielectric constant. D is the dielectric constant. E is the energy. Here, E1 and E2 represents the ions. Then R1 and R2 indicates radius. Okay. So from which we can derive the dielectric constant nature of the solvent. Clear? Yeah. Next, another characteristic feature is viscosity. If we really want to see, the viscosity of solvents, so one can easily define that what exactly is viscosity or not like that. A simple example I can give you. First one is water molecule, or you take water, and the other hand you take the honey. So if you really compare both the things, water as well as honeybee, so what happens? Honeybee is compared to the more viscous than the water. What exactly is this then? What's this viscosity tells about? Viscosity, like if you take the honeybee, the molecule or the solvent, honeybee solvent looks in a thicker manner. As soon as we place that honeybee upon the any flat surface, if the droplet is suddenly moves from upward direction to the lower direction, or if it takes more time, so that time I can call it as a highly viscous material or highly viscous solvent. If I place the drop of the water upon the flat surface, within a fraction of a second, that droplet is going to start travel from the upper part to the lower part in a fraction of a second. Here mobility is very high, means low resistance. In the viscous solvent, we can see the resistance is more. So where the resistance is more, that time we can call it as a highly viscous solvent. If the resistance is very low, that time we can call it as a low viscous solvent. So in all our organic reactions, especially in our chemical reactions, we're going to take the solvents which is usually having the low viscous solvents only. You take any of the solvents like for precipitation, for filtration, for so and so, we are going to take this low viscous solvents only. So now you can understand what exactly is viscosity, right? So this is all about the characteristic nature of the solvent. Clear? Yeah. So once if you understand like the characteristic nature of the feature of the solvent, that is one is lead boiling or melting point, then latent heat of fusion and vaporization, then the dielectric constant, then finally viscosity. After all understanding these things, like characteristic feature of the solvent, another thing comes, that is liquid ammonia. So basically we use this ammonia for various purposes to make the solutions like that, right? We'll come to know in the practical experiments, like when we are going to use ammonia, for what purpose you are going to use ammonia, like that. In this particular session, or in this particular context, or in this particular topic solvent, let us have some reactions of the liquid ammonia with other particular subordinates. In that first one, let us see the reaction of ammonia. And one more thing, if we talk about the liquid ammonia, it really has a very limited amount of the ionization value. Ionization is very low in the liquid ammonia. Means it is not as easily ionized in the water solvent, right? And it is liquid ammonia is stable at a room temperature for a longer time. So if we talk about the liquid ammonia, we should have a key point about this liquid ammonia is it has a low degree of ionization. Low degree of ionization. Then if you talk about another point, that is it is very stable at room temperature. Stable at room temperature for longer time. So this is the characteristic nature of the liquid ammonia. Correct. So if we talk about the structure of the ammonia, of course, one should know itself being a third semester students. We should not only have the simple the name of the molecules or any of the reagents. We should have the clear understanding, or we should have a clear idea about the structure, the story behind that the molecules. Example, story in the sense you might get confused that what exactly story the ammonia molecule has, that like that. Story in the sense should have clear idea about the structure of the ammonia. Like if we want to, so this is fundamental thing. Once again, if I'm talking about the valency theory, this seems very fundamental, but of course you should know this one. If I really write about this ammonia structure, so this is the ammonia structure having the two lone pair of electrons upon the nitrogen. So how one can write this ammonia structure? So as you all know that nitrogen atomic number is 7. If it is atomic number is 7, means I can write the atomic number as 2s2 2p3 2p3. This is the first shell, 2 electrons over, and another one is the second shell, 2 electrons, and again in the second shell of the p shell having the 3 electrons. Those three electrons will be shared by the hydrogen atoms here. We can see here. Second shell and second shell of the p orbital. If I write about the ammonia structure, NH, 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 two lone pairs, two electrons, unbonded or non-bonded electrons upon the nitrogen atom. You see here the three electrons here. This is from these three electrons from the p orbitals of the electrons 1, 2, 3. Right? If I talk about the hydrogen, atomic number is 1. I can write 1 is 1. So like that, in ammonia, 3 hydrogens we can find. So one of each electron we can find here. In very fundamental way, I can show you. Nitrogen is having 5 electrons like this. Hydrogen is also having the 1 electrons, that is 3 electrons. So this 5 electrons belongs to the nitrogen, and these 3 electrons belongs to the hydrogen. When we are going to make it as a bond, it is going to share by the 2 electrons from each atom or element, going to form as a ammonia. Now the question comes, why this is not in a parallel mode? Why in the pyramidal mode only like that? Here what happens? The bonded pair electrons here going to repel with each other. Going to repel with each other. So as you know that two same charges, if the two negatively charged atoms are there nearby each other, they are going to repel with each other. Example, you take a magnet. You take the same poles of the magnet. As soon as you place the same poles of the magnets, it is going to become what? Like repulsion is going to take place. In a similar way, in molecules also takes place. That's why the molecule of ammonia is in the pyramidal shape. Here bonded pair electrons repel with each other. That's why we are going to find in a pyramidal mode. Right? So this is the structure of the ammonia. So like this, you try to write the valency of all the atoms, whichever you are going to study in the upcoming classes. Try to write the structure of the molecules. So that gives particular understanding about the molecules. Especially in reactions, it really makes you much more helpful in reactions. Of course, in stereochemistry, like the structure of the molecules is really helpful in while studying the stereochemistry part. Again, the stereochemistry is another part of the section, that is the arrangement of the atoms in a space. What we are going to study, that is what stereochemistry. So in that one, we are going to study more appreciately this kind of concept. But in general, we should have clear idea about the like simple molecules, water. Again, if you take water is different shape like this. Here also we can find the 2 pair of electrons, which is non-bonded, which is unpaired electrons, going to repel with each other. So that's why the water molecule is in bind form. I think it's more than enough for you people to understand these 2 concepts. Of course, if I talk about majority of you people will know, being a third semester, might not be knowing the structure of the HNO3 as well as H2SO4. So have no idea about these structures about the HNO3, H2SO4, like what I shown now, like ammonia. So try to write the structure of those 2 molecules, HNO3 as well as H2SO4, and try to solve by yourself and refer any standard textbooks. I can suggest you to read the inorganic chemistry by, I think, if you really find in your library, that is J.D. Lee, inorganic chemistry by. Inorganic chemistry by. Hope you can see the name of the person, that is J.D. Lee. This textbooks really gives much more information about the fundamental nature of the inorganic chemistry. So try to find this book. Now you can find this textbook in online also. You take the textbook or you can download the textbooks from the website. you give simply online free textbooks like that. So that time the various websites comes in the respective or appropriate websites. You can type the name of inorganic chemistry by JDV. You will get a PDF file. You just download and read it. For the one who really want to understand the more fundamental based of about the elements or structure or molecules about the inorganic chemistry. And now come to the reactions of the liquid ammonia. So before going to talk about the reactions of ammonia, so we'll discuss these points that ammonia, liquid ammonia, how exactly react with the various subordinates with the environment. So that one we'll study in the further class, right? So if you really have any doubts within this topic that we studied till now, try to make a note and please share in the groups. I'm very free to again explain or to share the points about the same thing. Okay, thank you.